Hey everyone, thanks for coming out. My name's Emaad. I'm a senior data scientist at Datadog, where I'm working on the large model foundations and research team. We handle like foundation models, LLM, eval, that sort of thing. I'm going to be talking about Toto, which is our state-of-the-art time series prediction model. Acronym is Toto. If you don't know, at Datadog we really like dog puns, so Toto is the dog from The Wizard of Oz. This model is specifically optimized for observability data, which is a really important use case at Datadog. But we found that it's just a general purpose, awesome, all-around model. So if you don't know, Datadog is the leading observability monitoring platform for monitoring large-scale cloud applications. We collect all sorts of observability data across the whole stack, infrastructure metrics, application traces, logs, and more soon. And there's a lot of data, over 100 trillion data points a day. We ingest all in seconds, and we make it available with very seamless and clean visualizations, in addition to alerting and analytics. Overall, our goal is to have everything you need to run a high-scale application in production, all together in one site, seamlessly integrated in real time. As part of the platform, we have a few time series forecasting models. They're not ML per se, they're more like classical statistics. These are outlier detection. You can imagine if one host is behaving differently from the rest of your cluster, that's something you'd want to know. We have anomaly detection. For example, let's say service A, the latency is really high today, but the typical latency on a Monday afternoon is really different, and knowing that the traffic is highly seasonal, we can detect there's unusual activity on the server. And we also offer forecasts. So let's say we have a database, and can Datadog help me know when the disk is full so I can scale up or rotate the logs before hurting my quality of service? Now, the issue with these models is that they really there's three main issues. One is that you really need to train with domain-specific data and fit that to the model, which can be extremely limiting. You also have to do a lot of fine-tuning and parameter tweaking per time series, and that becomes a problem when we have over 750 integrations, 10 to hundreds of custom metrics where customers are just putting in whatever they want. So it requires an intense amount of domain knowledge. And oftentimes we have these things refer to as cold start problems, where you need a fair amount of data to make good predictions. And oftentimes that's not there, especially for short-lived cloud infrastructure like pods, hosts, and containers. So a time series forecasting model that we showed before might not have enough history to make a good forecast. So within Datadog, we use these time series for a few different types of products. The first we call Watchdog on the bottom left. And that can help you identify unknowns within the system. It'll typically alert the unusual activity and ping it out in Slack. We also have our Bits AI, which is our LLM-based investigative agent. It can detect errors, help you triage, recommend solutions, that sort of thing. And we also have Insights, which will take all this kind of time series forecasting information, give you kind of like a story of events that have occurred and how you might be able to address it. So given all these challenges, we asked ourselves, can we leverage all the data that we have to train a foundation model that can overcome these issues? And that brings us to our Toto pipeline. So high level, Toto is a multivariate zero-shot model, which means that you can clump in a bunch of related metrics together, and it doesn't necessarily need a whole lot of data to make a prediction. We're training on the largest data set that anyone has trained these types of models on. So previous models had used 100 to 200 billion data points, and we're training on the order of 1 trillion. And another thing is that it doesn't necessarily make a point estimate on a solution, where people in the field typically like probabilistic predictions. You don't necessarily want a machine to tell you an answer without telling you how confident it is in that answer. So Toto doesn't only give you an estimate on what the value will be at the time series, but it'll give you mean, standard deviation, what the distribution fitted to that is. In terms of data collection, we went across the Datadog pipeline, drawing from dashboards, notebooks, and monitors. This is all anonymized data. It's only time series, numerical data, and we group them together based on user-generated queries. That tells us which metrics are related and which ones aren't. Additionally, we're pulling from open source data sets, the main one being the LOTSA data set, which is a whole bunch of different time series. It's got like electricity and traffic and all these different things. And then we also generate synthetic data on the fly, which we found made our model more robust to noise. In terms of the training pipeline, we have our inputs that we pack together. We pass it through our model, which goes through an embedding and a transformer. It gives us our probabilistic estimation, and then we sample from that to generate our output series. And you can think of this kind of like an LLM. You give it a portion of a time series, it's generating the next steps successively in an autoregressive fashion. And our main contributions here were our transformer pipeline, which pulls apart the attention across the time domain and the domain of the different related variates. And we found that we can have pretty high-scale training in a more efficient manner than we would have had we used a traditional attention model. And we utilized this probabilistic mixture of student tease distribution, which was an idea that we came up with, and we later found that it's been played a lot with in the 90s. But it basically allowed us to fit highly complex distributions more accurately than existing methods had done before. In terms of our training pipeline, we do our storage and training on cloud infrastructure. We do our pre-processing in Apache Spark. And with Ray, we launch jobs for our training, and we track these all in MLflow. And additionally, we have integrations within Datadog to monitor every step of this pipeline. Specifically with Ray, we're deploying on Kubernetes. We emphasize security, so we're putting authentication on all of our clusters. And we also have a built-in observability Datadog Ray integration that we use. So in terms of results, as I mentioned, this was an observability optimized model. So we created a benchmark data set within our data that represented data that you typically see in observability settings. So think high sparsity, extreme right skews, seasonality, flat series. And we came up with these metrics which are robust to the large differences in scale you typically see in observability. So these are symmetric mean absolute percentage errors, or we call SMAPE, and symmetric median absolute percentage error, which we call SMDAPE. And we found that compared to the next best model, we were doing 8% better on SMAPE and 13% better on SMDAPE. Now, what's really cool is that we didn't specifically train for this, but we evaluated Toto on more general open benchmarks. We looked at the long sequence forecasting benchmark, which contains models, which a lot of models in this domain do. It's a compendium of data sets that talk about electrical transformer temperature, electricity, weather, across various forecast lengths. And we found that despite not actually being trained to do this, we were 10% better on MAE and around 20% better on MSE compared to the previous state-of-the-art models. So to us, this indicates that the observability data that we have at Datadog has a very different content from open source benchmarks that are out there, and it's extremely beneficial for time series forecasting as a whole. So we're really interested in scaling up the use of these models. We're looking to implement multimodality. More context is going to be really important for doing good at forecasting. This can be from text, but also other types of related metrics. We also want to be doing some kind of graph learning. There's a dependency graph that connects all these metrics, and ideally we'd like to inject that information in, make our model training even better. And I think a use case we're the most excited about is incorporating these into our existing LLM agents. So we have the Bits AI investigations. Using this kind of forecasting, they can be even better at like going in, making estimations on the types of situations that you're seeing, and helping customers to investigate and respond to incidents more efficiently. So if you're interested in any of the details of this paper, please feel free to reach out to check out our technical report, this QR code. We're also hiring pretty aggressively across all of these. So if you're interested in anything I've mentioned here, please feel free to reach out to any of the authors on the paper or check out the careers page and put in an application. And many thanks to everyone on the team. So me and Ben were primarily handling the modeling. Khan, who's right over there and can speak to anything regarding Ray or infrastructure pipeline. He did a ton of work on that. Charles, Elise, Yusuf helped with the evaluation and the data collection. And Uthman was our manager. Thanks so much. If you have any questions, feel free to ask. I can't hear you. Oh, yeah. Oh, so the question was, how did we ensure that our synthetic data wasn't significantly different from the training data that we were training on? Actually, we want it to be very different. We don't want the model seeing distributionally similar data because it's not going to be learning anything different. So we specifically, we're combining a bunch of different types of features that you might see in classical statistical like textbooks, but we knew that they wouldn't necessarily appear in any of our existing data. Yeah. Yeah, so the question was, is the time series foundation models at Datadog more focused on observability data or just general purpose? We found that despite optimizing for observability, it's better in both. So it's just a general purpose great model. It's focused on the observability, but it still does well, better than everyone else on the open benchmarks. Okay, I think we're good. All right, thanks so much, everyone.